So, we're going to be talking about inverse trig functions, and we're actually going to have to go backwards a little bit here and kind of talk about some of the stuff back in like section 3 before we started graphing. So, the first thing I kind of want to go over is what a function actually does. Okay? So, a function, I like to think of we have inputs and outputs, right? Okay. Like independent variable, dependent variable, your x and your y values. So I kind of like to think about it. If I have a function, sometimes people use the analogy of like a box. And I have an input, and then it goes into my function. My function does something to it, some type of operation, and then I get an output. Okay, and every function is like that. Okay? So I have an input and an output. With a trig function, so like for example, let's say hypothetically my function is sine. What type of inputs do I have? Oh, come on, guys. Not quite.
60 degrees.
Okay, that would work. Remember from my trig functions, my inputs are angles, right? If you think of sine of x, what are my x values, right? What I'm putting in, it's sine of an angle, right? We typically use radians, but degrees would technically work there. Does that make sense to everybody? The input to my trig functions is always going to be an angle, okay? So I'm going to put a value of like say pi over 4 in. Okay, so if that is my input, I put it in for x, and then what would the output be? Sine of pi over 4 is you guys are killing me. Square root of 2 over 2. It's a Monday, I guess. So, all right. So does that make sense? We've got a function. We have an input and an output. Okay. An inverse function, no matter what type of function I'm dealing with, this applies to stuff besides trig functions. But an inverse function basically reverses that process. Okay. So let's look at that. If I have an inverse function. An inverse function just basically operates backwards of this one. I will still have an input and an output. Okay. But in an inverse trig function, and that's where we have the -1, and we use this back in like the very beginning when we were solving right triangles. We did it on the calculator. You guys didn't really know how it worked then. But do you guys remember when we had like sine inverse of something? Okay. Well, we're going to be just looking at it as a function, right? Just sine inverse of x. My input for this is going to be a value or a ratio. And then my output would be what?
Pi over 4.
The angle, pi over 4. Okay? So it's basically the reverse process. Okay? That's why an inverse function will undo a regular function. Okay? Another example of that would be like kind of to go back and think about some other functions you guys are familiar with. Quadratics. Okay? So just kind of to, you don't have to write this down, but maybe just kind of help make sense of what we're doing. Y equals x squared, right? That's a function. If I put inputs in for x, so like 0 squared, my output's 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. right? Inputs and outputs. The inverse of that would be y equals the square root of x, right? These two operations are inverses of each other, and they will undo each other. So now, notice if I put 9 in for x, I get 3. If I put 4 in for x, I get 2. Right? So you can see how it kind of reverses from each other. Okay? Same idea, we're just going to be applying that to trig functions. So the main idea that I want you guys to get from that, though, is make sure we understand what your input and outputs are. So like with the x values and the y values. So with a normal trig function, so let's just do what we've been talking about, y equals sine of x. So for a normal trig function, my input is going to be an angle, typically in radians. And then my output will be a ratio, right? That's the ratio of the opposite side of the hypotenuse, or whatever trig function we're talking about. So cosine would be adjacent to hypotenuse, tangent would be opposite to adjacent. What we're going to be looking at is our inverse trig functions are going to look like that. And my x values, the domain and range, so you guys remember, I'm kind of going backwards to some Algebra 1 and Algebra 2 stuff. You remember talking about domain and range. Okay, we're going to have to kind of bring that concept back. Domain is like all the possible inputs that I can have. So everything that I can put in for x, and the range is like all the outputs, so all the possible y values. Okay, the domain and range of these things are switched. Okay. So the input here for x is going to be the ratios, and the output here will be the radian values, or the angle values. Okay. All right, so the next thing that we need to talk about is kind of going back to the unit circle, and you guys remember the different values at all the special angles that we looked at? I'm going to kind of sketch a quick unit circle. And I'm mainly just going to focus on these values in quadrant 1. Because remember, everything else is kind of derived from that, just different signs. So these values here in quadrant 1, all right, so those are our values for the special angles in quadrant 1. So this is 30 degrees, or what would the radian value there be? What? Pi over 6. This is 45 degrees, or pi over 4. This is 60 degrees, or, and then 90 degrees, or pi over 2. Good. Okay. So if we know those angles and values, we're off to a good start. Pi over 6, pi over 4, pi over 3. Okay. So just kind of give you guys an idea of how this is going to work. Let's evaluate some things real quick. So what would sine of pi over 3 equal?
A half.
Okay,
Square root.
Sine is going to go with the y value, so square root of 3 over 2. Okay. So now, let's look at the inverse. Okay. What would sine inverse of, and I'm not going to have an angle anymore if I'm doing sine inverse, what would sine inverse of a half be? Okay. Nope.
Pi over 6.
Pi over 6.
Sorry.
Okay. So again, kind of think, we're going to have to look at the unit circle or visualize it. But it's working backwards. Our answer to an inverse trig function will always be an angle. Okay? All right, so now let's maybe move outside of that first quadrant. Okay? So what would sine of negative pi over 4 equal?
Negative square root of 2 over 2.
Yep, negative square root of 2 over 2. Okay. And what would sine inverse of negative square root of 3 over 2 equal?
Pi over 6.
Close. Where would it be at? Would it be here, here, or here?
Oh shit. It would be closest to
Closer to the x-axis or closer to the y-axis?
the y-axis.
Okay. It'd be here, right? For that y value to be negative square root of 3 over 2. Now, I'm just going to tell you, for what we're going to be doing coming up, which I'll explain more in just a minute, instead of going all the way around, use the negative angle. So we're going to basically be looking at this, which is going to be negative pi over 3. Okay? One, it's a little bit easier that way, but we'll also talk about that in just a second. All right, so now we're going to be talking a little bit more about domain and range. And again, domain is all possible inputs for a function, and range is all the possible outputs. Do you guys remember talking about that back in like Algebra 1? Somewhat, hopefully? Yeah. So for something to be a function, part of the mathematical definition of a function, and let's just go ahead and write this down. So a function is a relation in which each input has exactly one output. Also, when we're looking at graphs, basically the same concept can be visualized through the vertical line test. Okay. You guys remember doing the vertical line test, hopefully, with graphs? Not so much? Okay. So maybe a quick demonstration. So it's easy to explain it on a graph, but if I have a function, basically I want an input to only produce one output, right? That's kind of what this says. What that looks like with the vertical line test, if I look at the graph, if I have an x value, so let me just kind of make a quick graph. You guys don't have to draw this. So get a different marker here. I can put another dot there. This would be a function, okay? It doesn't, we don't really have to understand the pattern or what type of relationship this is, but each input, each x value only has one corresponding y value, right? Okay. The vertical line test is just kind of a visual way to look at that. If I take a vertical line and pass through, it's only going to touch one point at a time, okay? So this would be a function. Okay. And what about that one? Okay. No, this would not be a function because it fails the vertical line test right here. Okay. The vertical line is going to hit 2 points at once there. Okay. Same kind of going back to the more written definition. This input, so my x value of 2 has 2 different outputs. Okay. And that's not good. Okay. So that's kind of part of our definition of a function. Okay. So the next thing that we need to talk about is when a function is what we call one-to-one. Okay. So one-to-one is kind of a characteristic that we can ascribe to a function if it is a function and its inverse is also a function. So it would be a function whose inverse is also a function. Okay. Let's think about some examples that may or may not be one-to-one. Okay. So first runner-up is just like a typical normal linear function. Okay. Would that be one-to-one? Okay. Yes, it would. Oh, I guess one thing I should add before we start looking at graphs. Just like we talked about the vertical line test here to see if something is a function, we can tell if the inverse is a function by the horizontal line test. Okay. So for it to be one-to-one, this is kind of like both. It would be, it must pass the vertical line test and horizontal line test. Okay. The horizontal line test would show that the inverse is a function. Okay. So if I look at just a normal linear function, yes, each input's going to have one output, and if I reverse that, each output would go back to only one input, right? The inverse would also be a function. Okay. If I look at, say, a quadratic, though, it is a function, right? And you guys know that, you're familiar with hearing quadratic functions over and over again, and we can see it would pass, these lines shouldn't be straight up and down at the edges, but we can see it would always pass the vertical line test, right? But would it pass the horizontal line test? No. That tells us the inverse is not a function, okay? If I had the inverse function, one output would go back to two different inputs, okay? Wouldn't work, okay? So, what about sine and cosine, where we had our wave? So, is it a function? Yeah, passes the vertical line test. Would its inverse be a function? No, because it would fail the horizontal, right? If I drew a horizontal line, it would hit 2 points. So the way it stands, the inverse for sine and cosine are not functions. Okay. I'll explain more about that. Okay, another way to kind of make sense of this is if I go back to the unit circle. Okay, if I'm looking at our normal trig functions, so sine and cosine. If I give you an input, which is an angle, you're going to get exactly one output, right? If I say sine of pi over 6, you get one value, right? If I say sine of 3 pi over 4, you get one output, okay? But if we go backwards, when I'm looking at the inverse trig functions, if I go all the way around my unit circle, if I said, well, where is sine 1/2? Okay, notice there's two different places that could happen. Okay, so what happens is, in order to kind of get around this, we have to restrict the domain. Okay, so for sine inverse, we have to restrict the domain to negative pi over 2 to positive pi over 2. Okay. So on this interval, sine is 1 to 1. Okay, meaning both like it is a function and its inverse is a function. The way that works, if we restrict it, you can think about it on the unit circle as only being the right half. Okay, so it's only this half of the unit circle. So on that interval, we're only going to get one answer. Okay, so this is kind of what I was talking about earlier with like the negative pi over 3. Because if I said, what is, we'll go through maybe a couple more examples here. So what are we on, example 5 maybe? Mm-hmm. Okay, so if I said, what is the sine inverse of negative square root of 2 over 2. The whole point of restricting the domain is that there is only one exact answer, okay, instead of having multiple, okay? So where on the unit circle, what angle would sine be negative square root of 2 over 2? Okay, negative pi over 4, right? Okay. Why could it not be, wouldn't negative 3 pi over 4 or 7 pi over 4 work?
It's out of the domain.
It's out of the domain. Okay. So the only correct answer here is negative pi over 4. Now let's take a look at cosine. So for cosine inverse of x, okay, we're going to have to restrict the domain as well, okay? But it's not going to be the exact same, okay? Because notice cosine here, I would have the exact same values, right? Because cosine is positive on the right half and negative on the left half, okay? So for cosine, we end up restricting the domain from 0 to pi, okay? Or what it ends up just being the top half of the unit circle.